Hi there, welcome to my channel Mandu to Fundu. In this video, I am going to discuss about the solution for finding the minimum absolute difference between any two elements in the binary search tree. Let's look at the problem description. We are given a root of a binary search tree and we have to return a minimum absolute difference between the values of any two different nodes in the tree. Let's take a look at the example 1. So here the difference between these two is 2, these two is 1, these two is 1, these two is 2. So the minimum difference is 1. So that's what this output is. And the example 2, here the difference is 1 and here it is 36, here it is 1. So the output will be 1. So the number of nodes in the tree will be ranging from 2 to 10,000 and the node values will be 0 to 10 to the power 5. Let's look at the approach to solve this problem. For example, we have the input tree 15, 10, 25, 21, 27. Okay. So for this tree, the expected output is 2. So the difference between these two is 5, these two is 10, these two is 6, these two is 2. So this is the lowest. So we have to return the output 2. Because the given tree is a binary search tree, if we perform the in-order traversal, it will produce the output which has all these elements in a sorted order. Then what we can do is we can find the difference between the adjacent nodes. Then we can finally report the lowest difference in that list. Okay. So first we'll have to initialize the minimum diff to the maximum value of an integer. Then we perform the in-order traversal. In the case of in-order traversal, first we visit the left and then the root and then the right. Whenever a parent node is traversed after processing its left subtree, then that parent node will be assigned to the previous node. Basically, for every node whenever we visit, we know who is previous. So for example, for 15, when we do the in-order traversal, when we traverse this node, we must have traversed the 10 before that. But for the 10, since this is the first element, there is no previous set. Okay. So if the previous is set, then we compute the difference between the current node and the previous node. For example, when we are here, the previous is point to 10. So at that time we compute the difference and check against the minimum difference variable. And we traverse the entire tree. Finally, we get the minimum value. Let's look at the flowchart. Input for this procedure is pointer to the root node and then address of the min difference variable and then address of the previous node pointer. First we initialize the cur diff to 0. Then we check whether the root node is null. If so, immediately return. And then we check whether there is a left child. If so, do make a recursive call to process the left subtree. So we pass the root dot left and min diff and the prev. If there is no left child, then we check whether the previous node is set already. If it is set, then we compute the difference between the current root's value and with the previous node's value and check whether this current difference is less than the minimum difference so far computed. If so, then update the minimum difference variable with the lowest value. If the previous node is not set, that means we haven't seen the first node yet. Whenever we come back to a node after processing its left subtree completely, then we have to set this previous value with that current node's value. And then if there is a right child exists, then we make a recursive call to process the right subtree. Otherwise, we skip and come out of the procedure. So at the end of the traversal, the min def variable contains the lowest absolute difference. Let's move on to coding. First I assign the max int value to the min difference variable, and then I declare the previous tree node pointer. Then I'm going to make a helper function call with the root node and the address of the min difference variable and the address of the previous node pointer. This helper function performs the in order traversal, and when we come back, the min def contains the minimum absolute difference. So I am defining the helper function. First I initialize the current def to 0. Then I check whether the root is null. If so, return immediately. Otherwise, if there is a left child present in this node, then make a recursive call to process that left subtree. Once we come back from the processing the left subtree, then so here I check whether the previous node pointer is set. If so, compute the difference between the current root node value and the previous node's value, and if that value is less than the min difference, then update the min difference. So the previous pointer is set when we see the first element in the in order traversal output. Then I set the previous pointer with the root node, and then if there is a right child exists, then make a recursive call to process that right subtree. Then I define that my abs function. So if the number is less than 0, then I multiply that by -1. And let me double check the code. Yeah, here I have to check against the null. So now I'm going to run the test cases. Okay, there is a compilation error, a typo. Okay, all the tests passed. Now I'm going to submit this program. Cool, it's accepted. Next I'm going to do the code walkthrough with sample input. So we have the input tree, which is 15, 10, 25, 21, 27. So the minimal difference is between 27 and 25, which is 2. So that is what we have to return. First, the in-order traversal begins at the root node. So every node will hit 3 times. One when we called from their parent, and then after the left child is done, one more time, second time, and then after the right child, third time. So I am going to show in the flow 3 times this node. First time when the node 15 gets hit, the min difference is set to the maximum max int value, and then the previous is null, and the current difference is initialized to 0. The moment we see the left child, we make a recursive call. So we leave from node 15. So when we leave, value will be same. Next we hit the node 10, and when we hit the node 10, the min difference still the max int, and the previous is not yet set, and the current difference is initialized to 0, but there is no left child. So what we do, we check whether the previous is set already. In this case it is not set. That means we haven't seen the first node in the in-order traversal output list. So that's why the previous is not set. So now this is the first node we are seeing. So the pre will be set with this node value. So that's what we are seeing here. And we are not computing anything because we do the computation only if the previous is set. Okay. So and also there is no right child. So this node will come back to the control flow will be coming back to the node 15. So that's what we are seeing here. So when we come back to node 15, the previous is already set to the node 10. So because the previous is set, we compute the difference, current difference. So 15 minus 10, 5, which is less than the max int value. So the min diff value is updated to 5, and after that the pre value will be set with the current node's value. So that's why we are seeing node 15 is set to the previous value. After this, next the right child will be processed. So we hit 25. So when we enter the 25, we see min diff, whatever was there when we leave 15, the same value will be here, except the current difference is initialized to 0. So when this node we enter, we see the left child is present. So we make a recursive call. So we are leaving with the same values 5, 15 and 0. So now we are hitting node 21 with minimum difference as 5 and previous is 15 and current difference is 0 when we enter. So when we leave, this node do not have any left child, so no recursive call, but previous is set with 15. So we compute the difference between these two. So 21 minus 15, 6. The current difference is 6, which is greater than the minimum difference computed so far. So we are not updating the min diff. And after that we update the pre pointer to point to this node. That's what we are seeing. The previous is set to 21. So once this is done, we come back to 25. So next we are coming back to 25 with the same value except the current difference is 0. Min difference is 5, previous is 21. And now when this node is we come back to this node, we see the previous is set. So we compute the difference between the previous and the current value, and the current difference is 4. So which is greater which is less than the previously computed minimum difference. So we update the min diff, and also we update the previous node pointer to the current node. So once after this processing done, we check whether there is a right child. Yes, there is. So then now next we'll have to visit the 27. So when we enter 27, the minimum difference is 4 and the previous is 25. So the current difference we compute zero. It's supposed to be 0. And so when we enter, the minimum difference is 4, previous is 25, and the current difference is 0. But when we leave, here we do the computation because previous is set, and we subtract the root value from the previous value. So 27 minus 25, 2, which is less than the previously computed min difference. So we update the min difference. So once that is done, we almost traversed all the tree, all the nodes in the tree. So this will return back to 25. I supposed to put the diagram for returning back to 25, returning back to 15, then returning back to the original caller, the get minimum difference. So finally, when we come back here, the minimum difference will be 2. That is the expected output. Next, I'm going to do the time and space complexity analysis for this solution. So let's do the time complexity analysis for this input. So there are 5 nodes and the expected output is 2. So in order to find the minimum difference, we have to traverse the entire tree. So the traversal is order of n time. So time complexity for this traversal is order of n. With respect to the space complexity, we are not allocating any additional space, but we are making a recursive call. So each call create a frame in the stack. So the maximum number of active frame for running this will be height of the tree. So which is log n. So the space complexity for this solution is log n. Thanks for watching this video. Have a great day.